Welcome in Mechanical System Design subject. I am Professor A.P. Godke of Assistant Professor in Mechanical Department. So today we will discuss about the gearbox design and what is the multi-speed gearbox or how the different spindle speeds are calculated for the machine tool gearbox. So why multi-speed are required? So that is the one of the important condition. So the different lathe operation need different spindle speeds. We know on lathe machine, turning operation can be performed, groove operation can be performed, threading operation can be performed. So the different lathe operations need different spindle speeds. So the different diameters cut needs different spindle speeds. So here in diagram we can observe that the spindle speed is inversely proportional to the diameter of the workpiece. So in this diagram you can observe the motor, then spindle of machine tool, then multi-speed or multi-stage gearbox is there. So this is the electric motor prime mover. This is the multi-speed gearbox. Then this is the chuck. This is the spindle of the machine tool, and this is the workpiece. This is a tool. Then this is the feed rate or feed direction. Then D is the diameter of the workpiece, and V is the cutting speed. So we know if the diameter of the workpiece changes, then the spindle speed required uh, is also going to change. So the spindle speed is direct inversely proportional to the diameter of the workpiece. So for different lathe operation, different spindle speeds are required. So that is the need of multi-speed. And then a different diameter like D cut need different spindle speeds. Means if you want to perform the different operation, then also we require the different spindle speed. And if you want to cut the different diameter size, then also different spindle speeds are required. So there is a need of the multi-speed gearbox in the machine tool. Next, why multi-speeds are required? Because cutting speed is calculated by using the formula V is equal to pi dn upon 1000. Therefore, the spindle speed is 1000 V upon pi d. Therefore, D is the diameter of workpiece at cutting location in mm. Means what? The diameter of if the diameter of the workpiece is going to vary, you require to vary the spindle speed. So there is a need of the multi-speeds in gearbox, or there is need to design the multi-speed gearbox. Then speed steps regulations are there. So we will get the different spindle speed steps. So the two types of regulations are there. One is a step regulation and second one is a stepless regulation. Then in stepless regulation, continuous speed range or speed steps we are getting. So in this graph, you can observe the continuous speed steps is given. So the range is very wide. In step regulation, discrete speed steps are there, or some discrete values are there for the spindle speed. So speed 1, speed 2, speed 3, speed 4. So up to speed Z, we can get the different spindle speed as per our requirement. So there is a certain progression or laws of progression is taken into consideration for step regulation or speed regulation. So to achieve the discrete or step speed steps, laws to select discrete speed steps, then progressions are there. So let N1 and N2 be the minimum and maximum spindle speeds to achieve in the Z number of intermediate step. Progressions are there used to find out the different speed steps and to find the relation between two speed steps. So the three laws of progression are used as a arithmetic progression, geometric progression, and harmonic progression. So these are these three laws of progressions are used to calculate the discrete or step speed values in the multi-speed gearbox. Then what is meant by arithmetic progression? Arithmetic progression is nothing but the difference between the two adjacent values is constant. That is nothing but the difference between two adjacent speed values. If it is constant, then such law of progression is called as a arithmetic progression. So let n1 is the n minimum. Similarly, n2 is the n1 plus a, where a is the difference of arithmetic progression, which can be calculated as a difference of n max to n minimum upon z minus 1, where z is the total number of speed steps, n max is the maximum spindle speed, and n minimum is the minimum spindle speed. So by using this formula, we can calculate the different spindle speed values. So n2 will be n1 plus a, that is n minimum into a. Then n3 will be n2 plus a, that is n minimum into twice a. Similarly, zth value for the speed is nz is equal to nz minus 1 plus a. That means n minimum plus z minus 1 into a. So that will be equal to n max. So in this way we can get the different spindle speed values by using the arithmetic progression. So the consider two intermediate speed steps ranges nk and nk plus 1. Corresponding to these, the diameters can be machine would be dk is equal to 1000 v upon pi nk, and dk plus 1 is the 1000 v upon pi nk plus 1. So the range of the diameter dk, delta dk can be calculated as a dk minus dk plus 1. So 1000 v upon pi gets common. So 1 upon n minus 1 upon nk. So that will be k is equal to minus 1. So you can find out the range of the diameter of the workpiece. So for example, now we will see one example. If n minimum is 30 rpm, n maximum is 385 rpm in 12 steps. Optimum velocity for the cutting tool is 20 meter per minute. Therefore, n minimum is 30, nz is 385, that is n max. Then z is equal to 12, v is equal to 20. Therefore, a is equal to n max upon n minimum upon z minus 1. So by using this formula, we will get the difference of arithmetic progression as a 32.273. Therefore, g is the, no need to calculate the g. So in previous step, so here the formula for the g is given as nk plus 1 upon nk. So the m different spindle speeds are calculated by using the standard method. So for first step it will be 30, second step it will be 62.72. Similarly for last step it will becomes as a 385 rpm. Similarly dk is calculated for the particular spindle speeds, and delta dk is calculated for the particular speed range. So in this way, we are going to calculate the delta decay, that is the range of the diameter. So in this way, by using the law of arithmetic progression, what we get the different spindle speed, we get the diameter, upper limit of diameter of the workpiece, and we get the range of the diameter of the workpiece. Now from the above table, it is observed that the arithmetic progression at low spindle speed, the diameter range is very wide, and hence there is no need to add more speed steps in calculated values, whereas at high spindle speed range the diameter range is very narrow, and hence some of the speed steps are redundant. So this is the conclusion part of the arithmetic progression, is that at low spindle speed diameter range is very wide, hence there is a need to add more speed steps, and in case of high spindle speed the diameter range is very narrow, and hence some of the speed steps are redundant in here. Next progression ratio, second is the geometric progression GP. So in geometric progression, ratio of any two successive spindle speed is constant and is called as a geometric progression. So phi is equal to n2 upon n1 is equal to n3 upon n2 is equal to nz upon nz minus 1, or phi is equal to nk upon n1. So in this way we can calculate the geometric progression ratio. Phi is equal to n max upon n minimum into raised to z 1 upon z minus 1. So same problem as follows. So phi is equal to n max upon n minimum raised to 1 upon z minus 1. So by putting the value, you will get the geometric progression ratio phi is equal to 1.261. Then for same, we are calculating the different spindle speed. So for first n minimum is 30, and for different values are 37.83, then 47.70, then 60.15. So similarly we'll get the final value for the 12th spindle speed is a 385. Then we calculate the phi for each speed, that will be the 1.264, that will becomes as a constant for each and every spindle speed. Then we calculate the upper limit of diameter of workpiece. So it will be 212.21 for first speed. Then similarly it will becomes as a 16.55 for the 12th spindle speed. Then we calculate the range of the diameter of the workpiece. So that will be the 43.92 for first speed, and similarly we will get 34.90, 27.02 for the subsequent speed of the spindle speed. Then decay is equal to 1000 into 20 by pi into 30. So that will be 212.21 is the first spindle, first diameter of the workpiece. So on comparison with arithmetic progression, geometric progression gives the better distribution of the speed. However, it is seen that At 2 RPM, still more speed ranges are desired, whereas at high RPM, some of the speed ranges are available, are not necessary. Means in geometric progression, there is some what advantages or better distribution of the speed we will get as compared with the arithmetic progression. Next, third one is a harmonic progression. In harmonic progression, the range between the any two consecutive speed range is same. That will be nk is equal to nk minus 1 upon 1 minus c nk minus 1. So c is calculated by using the formula n max minus n minimum divided by z minus 1 into n max into n minimum. So by using this formula, what we will get? We will get the nk and nk plus 1. So similarly, we calculate the different spindle speed using the formula nk minus 1 upon n 1 minus c nk minus 1. Then 5k will be the nk plus 1 upon nk. Then dk is calculated 1000 v upon pi nk, and delta dk is calculated by using the dk minus and dk plus 1 formula. So in this way we can get the different spindle speeds, then geometric progression ratio 5, then range of the diameter of the workpiece, and upper limit of diameter of the workpiece by using the law of harmonic progression. So from the harmonic progression, it is clear that harmonic progression gives better distribution of the speed in lower speed range. However, in higher power range, the speed ranges from 185 to 385. So huge speed distribution between the steps would mean uneconomical machining in this zone. Therefore, thus in harmonic progression, the speed values are spaced too wide apart, which results in non-optimum use of the tool. Now comparison of arithmetic progression, geometric progression and harmonic progression. So in arithmetic progression, constant change in speed at every stage is obtained. In geometric progression, constant gear ratio at every stage is obtained. And in harmonic progression, constant diameter change in every stage is obtained. Then low speed zone requires much more steps for optimizing machining in case of arithmetic progression. So low speed zone better than arithmetic progression, but still need a few steps in geometric progression. And in harmonic progression, high speed zones required much more steps for optimized machining. So this is the comparison of arithmetic progression, geometric progression and harmonic progression. Next one is the advantages of harmonic progression and arithmetic progression. So simple gear train arrangement is there in case of arithmetic progression and harmonic progression. Disadvantages of the arithmetic progression and harmonic progression are two shafts, that is the number of gear pairs are more in case of arithmetic progression and harmonic progression. Then increases the size of the gearbox with the help of arithmetic progression and harmonic progression. So these are the advantages and limitations or disadvantages of harmonic progression and arithmetic progression. So here in diagram also you can observe the gearbox design by using the harmonic progression or arithmetic progression. So the simple gear train arrangement is there. There are only two shafts. That is, first shaft is the input shaft and second shaft is output shaft. First shaft is connected with the electric motor so that the input speed is given to the input shaft. Then the second output shaft is end of the output shaft is connected with the spindle so that the desired speed can be given to the machine tool. Then the input shaft is the spline shaft so that the gears can be slide over the spline shafts and engage with the gears mounted on the lathe shaft or counter shaft, which is a fixed, or gears are fixed on the counter shaft. So in this way we can design the gearbox by using the arithmetic progression and harmonic progression.